Okay, so we're going to introduce the concept of electric potential, which is very similar to the concept of electric potential energy, which is also very similar to the idea of gravitational potential energy. And so to do this, let's start with the relationship between the force and some scalar quantity u, the potential energy, and notice that if we can write the force as the gradient of that function u, then we get a relationship which gives us the difference. If we integrate that over some distance, then we get a difference in u, which of course has to be equal to the integral of f over that distance, but that's the work. And of course the work is equal to a difference in kinetic energy, as we can show using Newton's second law, F equals ma. So I'll replace F with ma. I still have dot dr, integrate that over a distance. Mass is a constant, and we end up replacing a with dv by dt by definition, dotted in dr. Right, so we're trying to write this whole quantity in terms of velocity, so we can recognize that the mass is on the outside. I can think of this as dv dotted into dr and just move the dt over to the dr, but that of course is a velocity, so I have mass times the integral of dv dot v. And that gives me, oops, sorry, let me erase that. We are ready to evaluate the integral. So that's an integral in velocity, so we get mv squared over 2, and that gets evaluated from some initial to some final point, and of course that's the difference in a quantity we call the kinetic energy, where k is defined as 1/2 mv squared from our physics 1. And so sorry, I keep breaking my tip, we get difference in u, or minus the difference in u, equals the difference in k, which looks like minus u2 minus u1 equals k2 minus k1. So this is the same thing as k2 here. Let's bring the 2's on one side and the 1's on the other side. All right, 2 represents some final position or some later position. So the kinetic energy at position 2, we have minus u2 here, which, so if we bring it over to here, we get plus u2. And we get k1 on this side plus u1. And so we get this concept of the sum of k and u always being the same. And this we call energy conservation. The energy at 1 is equal to the energy at 2, where the energy is just k plus u, kinetic plus potential. Okay, so now let's think of the force that we're dealing with here, which is the electric force. So it's just q, the charge times the electric field. And the electric field is therefore minus the gradient of the potential energy per unit charge, right? We have to divide out the charge from the force. But we can also make this equal to minus the gradient of another function, which we call phi. It's a scalar function where u, the potential energy per unit charge, is what we we use the symbol phi again here, but this is not an electric flux, this is an electric potential. It's not an electric potential energy. So, right, if we integrate the electric field over some distance r, then that is the same as integrating minus the gradient of phi over some distance, and that's equal to minus phi. So we have that the electric potential is equal to minus the integral of the electric field over some distance. And so this is sort of similar to think of gravity. The gravitational potential energy, say, could be an object an object of mass m at some height h has a gravitational potential energy which is mgh. And if we think of the gravitational potential energy per unit mass, that would be the equivalent of the gravitational potential, right? That would be UG. Right, so very similarly, we have electric potential energy, and phi, which is that per unit charge. And the crucial point here is that when we consider a path that then takes us back to the initial point, then U2 is equal to U1, and the difference in potential energy is 0, but that's also true of the electric potential. And so we want a concept of electric potential energy difference per unit charge that is 0 along a closed path, and this will be a key principle when we get to circuits.